Hello, everyone. I'm Ruidong from Peking University. Today, I'm glad to share our work, DistRS, Disaggregated Reward Service for RLVR with batch-level constraint. This is the joint work of Peking University and ByteDance. Reinforcement learning with verifiable rewards, or RLVR, has become an important post-training paradigm for agentic LLMs. For many tasks, such as math, coding, searching, and games, we can automatically verify the model's output and convert the verification result into a reward signal. This allows RLVR to turn a model with only basic knowledge and capabilities into an agent with stronger reasoning, more effective tool use, and safer behavior. The workflow of RLVR includes rollout, reward, and training. During rollout, LLM generates output in an autoregressive manner. Then the output is verified and produces a reward. Finally, the data is consumed by training, which typically uses algorithms such as PPO and GRPO. Compared with a learned reward model, the reward here comes from an external verification procedure, which is often more reliable, but also much more complex and heterogeneous. This slide shows two examples of verifiable rewards. In CUDA code generation, reward computation may need to compile the candidate code and then execute it if the compilation succeeds. For online judge programming problems, the code is required to be automatically tested against the predefined inputs and outputs. So besides compilation and execution, it may also need to retrieve test cases from remote storage. So we can see that reward computation can consume very different resources, including CPU, GPU, network, and storage. This variability makes reward computation fundamentally different from a single reward model. To see why this matters, let us first look at RHF, reinforcement learning from human feedback. In RHF, reward usually comes from a forward pass of a reward model, which is another model inference workload. Because the reward model is homogeneous for all requests, we can batch requests effectively and often collocate reward computation with training and rollout. As a result, in RHF, the raw stage and the reward stage are executed in a sequence. Existing works also propose to fuse rollout and reward, or disaggregated rollout and training, and place reward model on one of them, which still assume that the workload of reward computation is very similar to that of rollout and training. However, RLVR is different. Each reward computation is independent, and different requests may need very different resources and execution time. If we still collocate reward computation with training and force batching in the same way, we can easily create inefficiency, contention, and blocking. So our first key idea is to treat reward computation as a service. We disaggregate it from the training workers, compute the reward at the request level, and allocate resources more flexibly. This service-oriented view is the starting point of DistRS. Before designing the system, let us first look at the workload. Here, we use a CUDA reward service as an example. The first observation is that the request arrivals are highly bursty. The reason is that reward requests are generated only when a sample finishes rollout. So within one batch, there are very few or even no reward requests during the training stage and the early part of rollout. Then, in the middle and especially the later part of rollout, many requests are produced in a short time. Furthermore, within a batch, there is also a long tail. This comes from the long tail of rollout. Most outputs are short, but a small fraction are much longer. So their corresponding reward requests arrive much later. The second observation is that the resource consumption of each request also changes over time. We can observe that the total compilation and execution time of each iteration increases as the training progresses. This comes from the shifted LLM behavior. As the LLM gradually learns to generate valid CUDA code during training, the likelihood that the generated code can be compiled and executed increases. In addition, a small number of requests may run for a long time. This occurs because the LLM may output arbitrary content. For example, the code containing infinite loops, so they may fail to terminate during execution. Typically, RL training sets a timeout threshold for the reward computing and stops execution once the time reaches the threshold. Let me now summarize the key takeaway from the previous observations. Faced with such a dynamic workload, a static reward service will lead to either wasted resources or stalled training progress. Therefore, we need an elastic, multi-tenant reward service. Elasticity allows the service to dynamically adjust the resource allocation in response to workload fluctuations, while multi-tenancy further promotes resource sharing and reuse. But this immediately raises the key challenge. What policy should govern scaling and scheduling so that we can achieve two goals at the same time, the high system efficiency and non-blocking training? The key insight is what we call requesting batch out. In this figure, each request is represented by a horizontal line, where the left endpoint marks its arrival time at the service. The length of the line is its execution time, and the right endpoint marks its completion time without queuing. Requests arrive and finish at different times, so the system operates at request granularity internally. But from the training side, their outputs are consumed by batch or mini-batch. In other words, what really matters is the completion time of the whole batch, not the completion time of an individual request. This leads to our second insight, batch level constraint and request level flexibility. We should define the SLO of reward service on batch level, and the batch level deadline is determined by the latest finishing request, which is the critical request shown here. Other requests do not need to start execution immediately after it arrives. It can be delayed as long as it still finishes before the batch level deadline. This request level flexibility gives us much more room to optimize resource usage without hurting the training loop. Based on these insights, we propose DistRS, an elastic and multi-tenant resource reward service with a microservice architecture. Each stage has its own worker pool, and DistRS makes scaling and scheduling decisions at batch granularity. This design separates concerns across stages while still optimizing for the batch level objective. Let me first explain the scaling policy for a single task. We scale at batch granularity, and the decision point is when the first request of a new batch arrives. The output of the policy is the number of workers allocated to each stage. Intuitively, using more workers can reduce reward completion time, but also increases resource cost. So we build the objective with constraints as shown in this slide. Formally, our goal is to minimize resource allocation while with minimal impact on training. Our solution is simulation-based search. DistRS evaluates candidate allocations using history workload information and picks the one that best satisfies the batch level constraint at low cost. Please refer to our paper for more details. However, there is still an important challenge, long-running requests. If allocation is decided only from history, one unexpected long-running request can break the batch level constraint. Here, we use an example with 5 requests and 1 stage to illustrate this problem. Based on history information, we only need to allocate 2 workers. Requests 2 and 3 will queue but do not violate the batch level constraint because request 4 is a critical request. However, if request 2 needs much more time than it estimated, it will violate the constraint due to queuing. As a result, 2 workers are not enough, and we need to allocate 3 workers in ideal. In summary, a long-running request with queuing may cause a deadline violation, so we need something much more robust than history-based scaling policy alone. A natural idea is to react after a long-running risk appears. But reactive solutions are too late. It is hard to detect a long-running request before execution, and timeout becomes visible only after queuing delay has already accumulated. Our approach is proactive and timeout-aware. We detect risk early by estimating the maximum latency if a request keeps waiting in the queue, and decide whether this would violate the constraint, and if so, treat the current allocation as unsatisfied and reallocate. Next, we move from one task to multiple tasks. In the multi-tenant setting, requests from different tasks are interleaved. Consequently, when a batch from one task arrives or completes, it is highly likely that batches from other tasks are still in progress. Therefore, scaling decisions should use both the current system state and historical information. DistRS combines the two, so it can respond to immediate contention while still leveraging workload regularity. For scheduling, our key idea is to order requests so as to minimize batch completion time. The baseline is FCFS, which is simple but ignores deadlines and contention across stages. DistRS instead uses earliest batch first, or EBF. It prioritizes requests from the batch with the earliest deadline, implemented with a priority queue at each stage. This reduces head-of-line blocking and better aligns scheduling with the batch-level constraint. Now let me briefly introduce the evaluation. We built a CUDA reward service testbed with each compiler using 4 CPU cores and each runner using 1 NVIDIA GPU. The workload consists of 6 IO training tasks for CUDA code generation, driven by the trace. We evaluate both resource consumption, including total CPU and GPU time, and extra delay imposed on each batch. First, we perform the end-to-end experiment on 6 RLVR training tasks. Under co-located IO training, DistRS reduces GPU time by 3.79 times and CPU time by 1.98 times. At the same time, the average extra delay is only 0.62 seconds. These results demonstrate that DistRS significantly improves efficiency while keeping the impact on training very small. Next, we zoom in on the effectiveness of resource scaling with a single task. We can see that DistRS reduces resource consumption significantly compared to zero queuing scaling policy, while still minimizing the influence on training compared to pure history-based scaling policy. This confirms that batch-level scaling with timeout-aware adjusting is effective for exploiting flexibility in reward computation. Finally, we evaluate request scheduling with 2 training batches, where batch 1 starts before batch 2. Using EBF, DistRS requires 1.5 times fewer GPU nodes than FCFS to achieve the same low extra delay of just a few seconds. This improvement arrives because EBF prioritizes requests from the first batch, which has a more strict constraint, enabling more requests from this batch to complete sooner and thereby reducing the overall extra delay. To conclude, we present DistRS, a disaggregated reward service for agentic IO training. DistRS is elastic and multi-tenant, and it leverages the requesting batch-out characteristic of reward service workloads. with batch level constraint and request level flexibility. It provides efficient reward computation while keeping training non-blocking. Thanks for listening, and I'm glad to take questions.